Hi everybody, welcome back to Chem 140. I'm just reading your comment about the font. If you message me in the Discord, I can send you the do you mean IT as in infotech, or do you mean it? Yeah, I mean, I have the file. I can send it to you if you need it. But if you can't like actually get it on your system or install it, then yeah, that's unfortunate. Okay, sorry about that. You use it on your personal computer though. We're gonna do chapter 8 today. Chapter 8 is very short. You will need a periodic table. If you don't have the link for P table, let me just grab that really quickly. Sure, that'll work. There you go. There's like a little bit of extra jargon at the end that doesn't really seem relevant. That's okay. You're going to need that, have that open for today because the entire discussion is going to be around it. Also, this chapter is extremely short. It is only 17 slides, so we're probably going to finish this within the first hour or so. We'll take a break, and after we finish, and then I will just allow like time for collecting questions. Oops, that's not what I meant to do. And if there aren't any questions, then we'll just reconvene tomorrow. We'll end class early. So today should be a nice short day. Things that are due either tonight or yesterday or upcoming or whatever. So last call for quiz number 3, which is units 4, 5, and 6, is tonight. Make sure you get that in before it closes or else it won't be counted. Lab worksheet number 2 is due tonight as well. That needs to be submitted to Canvas. That closes tomorrow. If you can't get it done tonight, you still have 24 hours. That's okay. Quiz number 4, which will be units 7 and 8, will go up after class today. I'm going to post an announcement with more details on that. Quiz number 4 is kind of special because it would close after the midterm, so it doesn't really make sense for me to hide the answers and then, surprise, here are the answers. Oh, also, I tested you on this on Friday. Like, that's not really cool. So what I'm going to do for that, and this will all be in the announcement, is that quiz will be, the results will be open. So when you finish your quiz, you will immediately get a score. You will get to see all of the answers. You can then take the quiz again, so everyone's going to do really well on quiz number 4. But quiz number 4 is super easy, generally speaking, anyway. So whatever. I would rather that you are able to see the questions if you choose to do the quizzes early so that you can be prepared for the similar questions. They won't be identical, but they'll be similar enough that you'll see on the exam for the content from those chapters. And then on Friday, the exam is units 1 through 8. Again, if you need to move your exam day, email me tonight or message me on Discord. I will move your exam date plus or minus 1 day, so you can take it on Thursday if you want, or you can take it on Saturday if you want. Any reason is valid. You do not need to supply a reason. You just need to tell me that that's what you want to do. If you don't email me by Thursday at 11:59 p.m. and it ticks over to Friday, then I have to say take the exam today if absolutely possible, because I can't start changing the date once the exam opens for you, basically. Like I can, but it's a lot more trouble than me setting a date, because once Canvas thinks that your date is this, I have to go through a bunch of hoops to tell it, oh no, I actually meant this, and it doesn't like that. So try and get those requests to me as early as you can. Okay, so let's talk about Unit 8. Unit 8 is all about the periodic table. The periodic table, which we'll just throw on the screen because I have it here. Oops, that's the wrong thing. Where is it? There it is. Okay. Just put it on the screen. There it is. Well, kind of. It's arranged in a very specific way. Some of this is going to be kind of outside of the scope of this class. We're going to get to that in 161 next quarter. But for now, we can discuss some of the traits on the periodic table and some properties that can be modeled by moving in a direction. So, for example, if I move from left to right, going through the elements that I do wherever I decide to examine left or right. There are properties that are common regardless of where I do that. So going up to down, same thing. So we call these periodic laws, and our purpose for this lecture is to discuss 2 of them. All right, so, well, actually 3 of them. I guess the first one is reactivity, but we're going to kind of gloss over that. Very early in the quarter, I want to say that we did this on the first day. I showed you a bunch of videos, or I should say you watched a bunch of videos because my foot was injured, and I gave you a lecture recording about sodium reacting in water and then a bunch of other elements. And you probably noticed that the periodic table is still on the screen. I should probably clear that. Actually, we're going to go right back to it anyway. You probably noticed that all the elements that I chose, so sodium, rubidium, potassium, sodium, potassium, rubidium, and cesium, these were all in the same column, and they all did something specific with water. When you drop them in water, they explode. And the explosions got progressively more and more explosive. We're not going to discuss the why behind that in this class. We are in 161. We talk about quantum mechanics because we can explain the reactivity of those elements and why it's so much easier for cesium to explode than sodium when we talk about electronic structure. But that's a 161 topic. That's beyond the scope of this class. But it turns out that elements that are in the same column on the periodic table have similar reactions under the same stimuli. So, for instance, if I put all the elements in group 1A into water individually, they should all behave the same. And they did. They all went boom. If I put all of the halogens in group 17 in contact with metal, they all corrode the metal. And you would also see a sort of reaction rate difference. Like the top one, fluorine, would be slow. The bottom one, iodine, would be very fast. And they'd all corrode the metal. Actually, I think it'd be the other way around in that case. Yeah, fluorine would probably be faster, and iodine would be a little slower. I'm thinking ahead. Not something that's relevant to this class, but anyway. So these are traits or properties that occur periodically, i.e., after X number of elements, we observe that trait again. And so a very smart guy realized this, and I believe I have his picture on the next slide. Yeah, there he is. This is Dimitri Mendelev. And what Dimitri Mendelev said about various elements and their reactivity was, I notice a trend here. I have every so often a certain pattern of reactivity. This element is reactive with water. This next one is reactive less with water, but reacts with acid or whatever. And let me get Mendelev's periodic table on the screen here, so that we have it here. So let's see if this works. Yeah, there we go. We'll just make this bigger. So what Mendelev did was he took a bunch of elements and arranged them into columns. And he said, okay, everything that reacts violently with water, I'm going to call it column 1. Everything that reacts violently with metals, I'm going to call column 7, or whatever. Now, you'll notice that some elements occupy the same box. And you might be thinking to yourself, well, copper doesn't react violently with metal. Or, I'm sorry, with water. I drop pennies in the fountain all the time to make a wish. It'd be really cool if every time you threw a penny in a fountain, it exploded, right? But that's not what happens. Same with silver and gold. When you sweat and get your gold or silver jewelry wet, it doesn't detonate on your arm. Thankfully, right? So there are some oddities in where he placed these elements with regards to reactivity. But in terms of their electronic structure and the formulas that they make, it actually lines up really well. And that'll be something we talk about more in Chem 161. But for now, this is how Dimitri Mendelev arranged his elements. Based on various properties, such as reactivity, ionic compounds that were formed with, say, chlorides or halogens, so on and so forth. Various things like that. And what he ended up doing was he had a periodic table with a bunch of holes in it. The holes are any of the elements that are pink. Mendelev only was aware of the elements that are in this kind of, what is this, blue-gray? Whatever color this is. And so he posited, well, wait a second. If I've arranged all the elements in these ways, but I have these gaps, perhaps I can fill in the gaps by describing what I would expect these elements to behave like. So, for instance, gallium. Gallium's a good example. He expected gallium to be similar to aluminum and indium because they were in the same column. And so it should have this density, which is roughly between them. It should have this formula when it forms a compound with chlorine. It should have this melting point. It should have this physical whatever. These different traits. And it turns out the predictive power of his periodic table was so useful that they started to discover elements that had been previously unknown to everybody, really, until that point. And so those were discovered in part to the periodic table that Mendeleev had developed. So that's really cool. Aquamarine. I guess that could be aquamarine. I thought aquamarine would be like a little prettier. I mean, it's a gemstone, right? So I don't know. Now, today we have arranged Mendelev's periodic table a little bit differently. So you can see that we don't have any of this nonsense where we have multiple elements in the same spot. Instead, our periodic table is stretched out so that every element gets its own box and there aren't any duplicates. And we've also renumbered the groups. And so that looks like this on my periodic table on the screen. We know today of up to 118 elements, from hydrogen to oganesson. Oganesson being 118. My picture doesn't show the last few because I took this picture, or I copied this from the internet in like 2009 when I wrote this slide, because I reused some of my slides from ancient times when I was a first an instructor. And back then, the elements had not been discovered, and some of them hadn't even been named. So you could see down there, starting at 110, it says nilum, and then 111 is unium, which is just fun to say. We eventually gave all of those elements names, which you could see on the screen when I do that. There is a naming process for elements that have been discovered, and that naming process is based on nominations for either places that were important in discovering the elements. So, for example, over here we've got moscovium, livermorium, and tennessine. Moscovium probably being Moscow, I would assume. Livermorium being the Lawrence Livermore National Laboratory, which I grew up practically next to. It was an hour away in California. And then tennessine, I think there's a particle collider in Tennessee. But they must have been essential in doing this because Tennessee now has... There are only 2 states, as far as I'm aware, on the periodic table. One is Californium, down here, and the other is Tennessine, which I kind of like Tennessine. It rolls off the tongue. Why are some of the AMUs in parentheses and some are not? The ones in parentheses are radioactive, and the parenthesis AMU is the stablest isotope. It has the longest half-life. So tennessine 294 is the most stable isotope of tennessine, for example. With technetium over here, it's technetium 98. That's just what those mean. There is no atomic weight for those elements because they don't last long enough for you to get an accurate number. Like if you were trying to weigh it and it's decaying away and it's getting lighter as it does so because it's ejecting particles, you can't figure out how many grams there are in a mole, or how many AMU there are. So, all right. We're going to categorize the periodic table into 2 dimensions, and I'm going to put those both on the screen right now. The first dimension is called the group. Groups run up and down, and the groups are numbered along the top. 1, 2, 3, 4, all the way up to 18. Some groups have names. We're going to come to those names in just a second. Going left to right are periods. Periods are numbered from top to bottom here. So period 1 has hydrogen and helium in it, and that's it. Period 2 has lithium to neon. Period 3 has sodium all the way to argon, and so on and so forth. The only oddity that occurs with periods is that in period 6, there is not enough space on the periodic table to fit this in. So when you get to barium, the next step is you go down to this row down here to lanthanum, and then you go all the way across, and then you back up, and then you continue across the periodic table. Same thing with period 7. You go radium, actinium, thorium, and so on, all the way to lawrencium, and then keep going. So that is a space constraint issue. We could have put all of that in the same row, and then there would just be a giant gap right here. Kind of like this gap is right here in the periodic table. But then the periodic table would be extremely long, and selling posters of it for the classroom would be cumbersome. So it was purely a financial thought, I assume. Now, what do groups and periods tell us? For our purposes, groups tell us things about reactivity, and periods tell us things about electron energy. We're going to talk about electron energy in 161 and 162. For the purposes of this class, though, there is an important trait that we're going to discuss in Unit 9, which we're going to start next week, that involves the periods and the groups. We'll cross that bridge when we get there, but it has to do with electrons. In fact, the entire structure of the periodic table is based around electrons, because electrons, it turns out, are the most important feature of chemistry. All chemistry is based on electrons, believe it or not. All right, I guess I'm not clicked over there. There we go. On the screen, I have a bunch of labels for various regions of the periodic table. Oh, why did I put the tablet away? That was weird. I'm not done with class. I taught the previous class and I put the tablet away, so I got to get this back. There's really only one modification that I want to make on this, and that is to change where it says inert elements. I want to call this noble gases. We'll even give them a little crown here, so... Or maybe more like a chef's hat. There we go. We'll give them the onion crown. So I'm going to start at the left. Group 1, or 1A. I'm going to actually number these like this. I mean, I guess I could number them down here, so I'm not writing over that. Group 1 is known as the alkali metals. Group 2 is known as the alkali earth metals. You might also see these called the alkaline... Where's my cursor? Earth metals. Both of those are used pretty much regularly. And the reason that they are called this is because when you add them to water, you make a basic substance. Basic meaning it has a high pH. It's the opposite of an acidic substance. And something that is basic is also known as alkaline. So that's where the name comes from. In the middle, groups 3 through 12 are the transition metals. These are just the transition from the left side of the periodic table to the right side of the periodic table. Believe it or not, that's the reason they're called that. Groups 4 through or 13 through 16 don't really have much of a name. I have written the nonmetals and then other metals on there just because we're going to talk about metallic character in just a bit. So we'll come back to those a little bit later on. But the important groups on the far right are halogens, which are elements in group 17, and the noble gases, which are in group 18. We know already that noble gases, like all nobility, sit on their asses and do absolutely jack shit, right? In chemistry, noble gases don't react. They do nothing. They just hang out. They bounce around, but they don't do reactions. Now, like all things in chemistry, there's always exceptions. I'm looking at you, Xenon. But generally speaking, that trait is true. Noble gases are inert. Finally, down here at the bottom, the rare earth elements actually belong in this gap right here that I'll just draw really thick. And some terms that are relevant to these are lanthanoids and actinoids. You may also hear those called lanthanides and actinides. Again, those terms are pretty much interchangeable. And so this would be this row and this row right here. So really, the gist of this slide is learn these group names and region names as is necessary, because on a quiz or exam, I might ask you, select the noble gas from this list, or select the alkaline earth metal, or put these in the correct category, or whatever. All right, so talking about the metals, so there's that region where we had like non-metals and other metals and stuff like that. Using the periodic table, we can actually categorize things by metallic character. And so the general rule is that all the metals are on the left and the non-metals are on the right, and then there's this Goldilocks region in the middle where the properties that align are just right, and they behave sort of like a metal and sort of like a non-metal in various ways. Now, we're going to define metals and nonmetals in a few slides here, but for now, we'll just look at this picture. Anything that exhibits metallic properties is going to be found on the left side of the periodic table. Those are the tan squares, we'll call them. Elements on the right side, the blue squares, are nonmetals. And then there's this staircase, which I can't draw in red because that's not going to work. So I'm going to draw it in purple. Purple is good. I'm going to try and draw over this so that it is more obvious by the fact that I'm drawing scribbly lines everywhere. There we go. This is known as the metal-non-metal staircase. Not every periodic table has it. Unfortunately, the P table doesn't draw this in super well, if it draws it in at all. But basically, everything that touches the metal-non-metal staircase, with a few exceptions, is a metalloid. So those exceptions that are important are aluminum, and that's really it. Polonium and acetine, not super important. I like to remember aluminum and polonium because then you can make the joke Alpo, which is a dog food, which comes in a metal can, so they're metals. But astatine kind of ruins that, and nobody gives a shit about astatine anyway. It's super radioactive. It doesn't last long. So yeah, metals on the left, non-metals on the right. Metalloids touch the line. So now it falls to us to define these. What do these terms mean? We're going to define a metal as any substance on the periodic table that has all of the following properties. So it has to have all of them. And those properties are the following. High thermal and electric conductivity. What does that mean? What that means is that if you were trying to apply heat to it, it would heat up very quickly. And it would heat up thoroughly. So like a cast iron skillet, if you put it on your stovetop, it heats up very quickly and the heat is distributed evenly because it's able to conduct it very well. Electrical conductivity means that you can conduct electricity and it will pass through it. For example, copper wire, which we use for all of the wiring for electricity in our houses and buildings and stuff like that, is a very good conductor. The other properties of metals that we care about are that you have to be able to shape them in some way that they retain their shape. And so those are the properties of malleability and ductility. Something is malleable if you can hit it with a hammer and all it does is deform and not break. For instance, if you hit a chunk of pure aluminum with a hammer or apply force to it, what it ends up doing is getting squished. And it squishes itself out into a bigger and bigger and bigger surface area, but the whole thing remains a contiguous piece of metal. So if you want to make aluminum foil, what you actually do, and this is what is done, is it is squished by a press until it is the thickness that is desired, which is generally like 60 micrometers or something like that. I don't know what it actually is off the top of my head. But it's very small, or it's very thin, and then it's one contiguous piece of aluminum foil. You can easily tear it because it's thin, but the process by which it is made demonstrates that it's malleable, because it doesn't shatter it into a bazillion pieces. Something is ductile if you can pull it in one dimension and it becomes a wire of decreasing radius. For instance, if you have a 0 gauge wire of aluminum and you pulled on it with some sort of device that could exert a lot of force, you could reduce the gauge of the wire to make it like 4 gauge or 8 gauge or 16 or whatever application you needed it for. Gauges of wire, as the gauge gets higher, the diameter gets smaller, for what it's worth. Gauges are also used in like body piercings. So like earrings, or like if you pierce your nose or whatever. So that's just where that term comes from. The last property of metals is that they must be shiny. Now, that seems kind of like why are we including this? This is kind of silly. But a property of metallic bonding is that electrons are mobile, which is why metals are very conductive of electricity. But the result of that electron mobility is that when light bounces off of its surface, it is reflected essentially in the same state that it was absorbed. And so the end result is that you see luster. If you have a very well-polished piece of metal, the end result of that is actually a mirror, and all the light gets reflected. So we use mirrors, which are made of very, 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 very thin pieces of, not pieces, but like sheets of a metal. Usually silver is the metal of choice because you get the best quality image. You can make a mirror out of most metals. For example, you can make a bronze mirror, but because bronze is kind of a ruddy, reddish orange, or copper is ruddy, reddish orange, bronze is more orangey brown, I guess. That color would tint the image that you see. So it'd be like looking at a sepia tone photograph, I guess. I've included Bender because he frequently says, "Bite my shiny metal ass." That is evidence that he is a metal. What are the James Webb's telescope mirrors made out of? I don't know off the top of my head, but my suspicion would be silver. My next guess would be aluminum because it's much lighter, and weight is very important for something of that size, being that it's in space, but I don't know off the top of my head. I could tell you how it's made by aerosolizing a metal and letting it plate out in a essentially monoatomic layer to get a perfect mirror. But I don't know which metal is used for that. Unfortunately. I bet you could look it up, though. I bet if you typed it in Google, somebody would know. Alright, so those are all of our properties of metals. Remember, to be a metal, you have to have all those properties. If you are not a metal, you exhibit none of these properties. So, for example, iodine does not conduct electricity or heat well. In fact, it basically sublimes the second that you put any heat to it. If you hit it with a hammer, it doesn't turn into a thicker sheet. It just shatters. Oh, beryllium. I wouldn't have guessed that. Interesting. And it's definitely not shiny. Charcoal is another non-metal. It doesn't conduct heat well. It reacts, actually, if you heat it slightly, which is why we burn it for things like barbecue. And then it tastes delicious. And then finally, we have metalloids, which have some of the properties, but not necessarily all of them, to varying degrees. For example, on the screen, I have silicon. Silicon looks pretty shiny, as shown in the picture. However, it is not a great conductor of electricity. It is it is not a complete insulator. That is, it conducts some electricity, and that is actually very useful for us because in a circuit board, to create a logic gate, we want to control the flow of electrons. We don't want them to flow randomly in all directions. That would not allow us to create a circuit or a logic gate. So we can exploit metalloids for various purposes because they are in that in-between region. And that makes them very, very both interesting scientifically and practical and valuable economically. Earlier, I told you about the periodic table, how if we stretched it out, it wouldn't fit on a wall, and so we couldn't sell posters to colleges. This is what it would look like if the periodic table had the lanthanides and actinides in the spot where they probably should go. So I'm just showing that to you just as a curiosity, just in case you wanted to know. You'll notice that there are 3 hydrogens on this table. Don't ask me why, I don't know. Alright, so what I want you to do is, given these elements, we'll number them here, so 1 through 5. I want you to find the element on the periodic table, and in the chat I want you to write the name, the period it's in, the group it's in, and then give a category that describes it: metal, alkali metal, halogen, noble gas, transition metal, lanthanide, actinide, whatever. And then finally tell me if it's a metal, non-metal, or metalloid. I'll leave you about 4 or 5 minutes to do that. You will need ptable.com. And we'll go over the answers at the end of that time. So I'll see you in a bit. All right, 1 or 2 more minutes. We'll go over the answers here. All right, so let me get... How am I going to do this? Oops, that's the wrong window. Sorry, I was checking to see how many people were watching. There we go. That'll work for now, I guess. Okay. I'm going to write the answers behind this, so you aren't going to be able to see them just yet. But I will say them. So let's click on fluorine here. So here's fluorine. It's over here in the corner. So fluorine is in group 17. You could also write 7A. That's fine. I'm going to just stick with the IUPAC numbering scheme, which is shown on the screen there. It's in period 2 because it's in the second row. And then I want to give it a category, so that would be halogen. And then I want to classify it as a metal, non-metal, or metalloid, and it is a non-metal. All right. Then we got to find calcium. Calcium's over here. Calcium is in group 2. And it's in period, I want to say 4? 4, yeah. It is an alkaline earth metal and a metal. All right, next we got krypton. Krypton's over here. Krypton is in group 18. I don't remember what period it's in. 4? 4. It is a noble gas and also a nonmetal. Then we have Au, which is gold. Latin name for gold is aurum. And that is in group, I don't know what group that's in. 11? Period 6, I want to say, yeah. And it is a transition metal, and of course, having metal in its descriptor, it is also a metal. Thorium's down here at the bottom, number 90. Thorium is named after Thor, the Norse god of lightning. If you played God of War, you know who Thor is. Let's see here. Actually, I don't know. Is he in the new one? I mean, he was mentioned in the previous one. I don't play the games. I just sort of watch and read about them. So, anyway, there is no group number for a lanthanide or actinide. It looks like they're in group 5, but in reality, these elements, again, they kind of go in this gap right here, and this gap does not represent group 3. So they don't really have a group. So all of these elements have no group down here. So kind of a trick question there. But it is in a period, and that period is period 7. And it is an actinide. Or you can call it rare earth. Rare earth is kind of a weird name because a lot of those elements aren't very rare. Like uranium's absolutely everywhere. and it is, of course, a metal. So I'm going to close this thing, and there's my solutions for you. So you pause the video and copy those down if you haven't done so already. But there you go. All right. I can't believe we're already almost an hour into the lecture, so I do have a little bit left to do. So what I'm going to do is we're going to take our break now. So we'll put this on the screen. I don't know where my timer went. There it is. We'll get the music going again here. And... oops, hold on. That didn't work for some reason. There we go. Okay. So yeah, we'll get the music going. Let me start the timer so I actually remember. I didn't start the timer for like 2 minutes earlier, so. Yeah, we'll get the music going, and I will see you in 10 minutes. So, back in a bit. And we're back. Alright, I hope everyone had a good break. Filled your water, pet the cat, make a bagel, you know, that sort of thing. Let's see here. So the next section we're going to talk about two trends on the periodic table that are going to be very useful to us in 161. Right now, they're sort of just kind of things that are going to be like, oh, well, that's interesting, I guess. One of them we already started talking about. It's metallic character. We're going to show visual examples of that. But the other one we're going to talk about is atomic size. And again, atomic size is not going to be super relevant to us in this class. It's just going to be a curiosity. But in 161, when we talk about quantum mechanics, atomic size is actually an extremely important property that governs practically all of how chemistry works. The other property is effective nuclear charge. Again, those are things we're going to talk about in 161 in Chapter 3. So, we'll introduce it now. So, first, let's talk a little bit more about metallic character. So, you might have noticed that if all the metals are on the left and all the nonmetals are on the right, well then, duh, going from right to left means things become more metallic. I have shown you visual examples of those on this slide. So, this is elements along period 3, which we can... Oh, that's the music I'm playing. Hold on. There we go. So if we go along period 3, so here's chlorine. Chlorine, if I hop across, I'm just going to go chlorine, hop to phosphorus, hop to this. I'm basically going in steps of 2 elements at a time here to get the pictures of them. And you can see, oops, that's not the right button. There we go. You can see that obviously things become more metallic just by virtue of them becoming a solid at first. And then they start to take on the metallic sheen and luster that we're familiar with metals. So this is left to right. This trait also works top to bottom on a periodic table. So here's group 15. So if I go back over here again, so this would be nitrogen, phosphorus, all the way down to bismuth. And elements that are at the top are less metallic than the elements at the bottom. I don't know if you've ever seen bismuth, but it glimmers like a rainbow. Probably the most popular rendition of bismuth is Steven Universe of all shows, and they actually get her gem very accurate. Like, somebody went and did their research. Bismuth looks like her gem. Or, bismuth's gem, I should say, looks like what bismuth actually is. But at the very top we have nitrogen, which is a gas at room temperature. I'm showing it in a flask as a liquid that is very rapidly boiling and evaporating at room temp. Then we have phosphorus again. Arsenic looks a little more metallic just by virtue of it being a shiny gray. Then we have antimony, which looks very metallic. It almost looks like crumpled up aluminum foil to me. And then bismuth is extremely shiny. So that's metallic character. We've already talked about that enough. Let's talk about atomic size. Atomic size is determined by the distance of the nucleus to the furthest electrons away. And I am giving you these values in picometers because that's the reference that I got. You might see these in angstroms in other places. Hydrogen is incredibly tiny. It is 1 proton and 1 electron. Those electrons the electron in hydrogen has no other electrons that it has to compete for space with, so it hangs out real close to the nucleus. By the time you start adding even 1 additional layer of electrons, you have to start spacing them farther and farther and farther out because electrons repel each other. You can't just jam them all in close to the nucleus. So each time I add an extra layer of electrons, the atom size gets bigger. So as you go down the periodic table, atomic size always increases. And the jumps are large at first, and then they kind of slow down. And this is because adding a little bit of radius at a high volume, when the radius is much bigger, it doesn't take much radius to add a lot more volume or space for electrons to inhabit. So that's an easy trend to rationalize. I'm putting more electrons. They have to go further away because I just don't have room to put them closer. Okay, we could do that. Now, by the same logic, you might think that, okay, as I go left to right on the periodic table, I'm adding more electrons, so it should get bigger going left to right too. And it turns out that the opposite is actually true, believe it or not. This is period 3. And as I go from sodium across the periodic table to argon, the atoms actually get smaller. And the reason for this is because not only am I adding electrons to my atoms, and those electrons are inhabiting mostly the same space. Like, I'm not adding a new layer going across the periodic table. These electrons can fit roughly the same distance, and they do repel each other, so it should get a little bit bigger. But I'm also adding protons when I do this. So the number of protons and electrons here, so this is 11, 12, 13. Every time I add an electron, I also add a proton in the middle. And the protons pull the electrons toward them because they're attracted, right? And it turns out that if I'm adding one electron that is roughly the same distance as the rest of them, but also adding a proton, the effect of the protons wins. And so atoms get progressively smaller and smaller and smaller despite me adding electrons. We're going to codify this in 161 in more detail. But for now, all you need to know is that if I go left to right, atoms actually get smaller. It's counterintuitive because everybody is like, oh, electrons always repel, so they should always repel from each other. But don't neglect the effect of protons. There's competing forces here, and this is the bigger one, and it wins in this instance. And so that's what this is saying here. We're going to talk about this property down here, effective nuclear charge, in 161. Effective nuclear charge and atomic radius are the two main factors in quantum mechanics that we care about. So you'll see it more then. For now, you just need to memorize the trends. Going up and down, atoms get bigger as you go down. Going left to right, atoms get bigger as you go left and not right. Atoms get smaller instead as you go to the right. All right, so the last exercise that I have for you on this slide, before we call it a day, or gather any questions here, I want you to identify which of these atoms in each pair is more metallic and which is bigger. You're going to notice that it's the same answer for both, because the trends work out that way. Something is more metallic if it's further to the left and down, and the same is true for size. So circle the atom that fits both of those properties. Once you've done that, if you have any other questions that you want me to answer, because this is the end of Chapter 8, I believe, we can do a short review, or we can just save it for tomorrow. We can convene early. It's up to you guys. So I'm going to give you like 2 or 3 minutes to do this. We'll go over the answers in a bit when I come back. All right, one more minute, we'll go over the answers here. All right, so what we'll do here is let's get this back on the screen. And you know what? We don't really need this part. I can't see the chat, or you can't see the chat. I can see it on my window here, but that'll be okay for now. So we're going to pick the elements that are further to the left and further down, because they will be the ones that are more metallic and also larger. So I'm going to look at chlorine and sulfur. So they are adjacent to each other. Right here, I'm highlighting both. Which one's further to the left or further down or both? And that would be sulfur. So sulfur must be more metallic and also larger in terms of atomic size. Just in case this wasn't clear, I mean, because we are working this. When I say larger, I mean in terms of atomic size and radius, not by mass. Just FYI. For the next one, we got gallium and indium. They're right here. Which one is further left or further down? That would be indium. So it is more metallic and also larger. Then we got magnesium and aluminum. So there's a big gap between these two. But the periodic table doesn't really reflect that gap in any physical way. That is just a gap for our purposes. So same rules apply. Which one's further left or further down? That's magnesium. Then we got calcium and potassium here. Right here. Which of those is further left or further down? Well, that's good old potassium. And then finally, we've got barium and radium. And even though it's radioactive, which one is more metallic? Well, while it's radium is more metallic than barium. All right. I believe that just about does it. So first we'll do this, which means I got to turn the audio back on here for the hooray. And that's all I got. So let's talk very briefly. Can I draw on the end of slide sheet? Can I? Oh, no, I can't. So I got to actually go back to here. Can I remove that? I can do this. Okay, this works. So let's very quickly write down like what the agenda is for the rest of the week. So tomorrow is a review session. And what I want you to do is bring me any questions you might have. Problems to go over, either from the worksheet, workbook. Try not to ask too many lab questions. I will answer lab questions, but the point is that we're trying to prepare for the exam. If the lab questions are relevant to the exam, then sure. Like if you want me to do a density calculation. If you ask me to show how to calculate the thickness of aluminum, I'll ask you to put that in the Discord and I'll answer that in there. I want what's on the air, on the video, to be relevant to the exam, specifically. Is there a correlation with atomic size and metallic character? The trends themselves are similar. So there is a correlation. I don't know if there's a causation there. So yeah, they do correlate, but things are not more metallic because of their size necessarily. There are other factors in play. We'll talk about that more in 161, I think. So that's Wednesday. That's the review. It will be as long as you want it to be, up to 2 hours. If there aren't questions, then I take the stream offline and we call it a day. You can still always ask me questions in the class Discord. That's totally fine. Friday is exam number 1, which is units 1 through 8. I have the exam open for 24 hours on Friday. You may take the exam at any point during that 24-hour period. Like all online assessments, you get 2 attempts in case your power goes out during the first one, or if you just want to take it again to see if you could do better. Totally fine. I will also move it for a specific student by student basis. If you email me and request to move your exam to either Thursday or Saturday, email me and I will do that. That is very easy for me to do early, but you have to let me know that by Friday. And obviously, if you let me know on Thursday that you want to take the exam on Thursday, that might cut down on the amount of time that you have. So make your request early, and I will get to it. I guess the last thing that I mentioned earlier in the period, I don't need to write it here. Quiz number 4, which is unit 7 and 8. I'm going to go and open that after class today. I will set it so that the quiz is open results. So when you take the quiz, it will immediately show the correct answers and your score. But other than that, I don't think that there's much else that I need to say. So make sure that you are prepared for exam number 1. All of the topics that I have at the beginning of each slide, so like where it lists like the sections, you should know the main concepts from each section. Have any notes or conversions or the periodic table or whatever handy before you start, and you should be in good shape. All the rest of the information is in the syllabus about the exams, and you can read it there. Do you want me to email it? So if you send it to me in Discord, I will then do it. I will take care of that probably immediately, so you're okay. If you don't get a notification from me through Canvas that says exam date changed or set or whatever, let me know, because that means that I didn't hit a button or something didn't go through. How long is the exam? I want to say it's like 30-something-ish questions, between 30 and 40. And you get however much time it says on the syllabus. I want to say it's like an hour 15 is what I give you. Something like that. I don't know off the top of my head, though. All right, that's really all I got. So make sure that on top of all of your studying, you turn in quiz number 3 if you haven't done so already. It is due tonight. Or it's due yesterday. It closes tonight. And lab worksheet number 2 is due tonight, closes tomorrow. Is the review session at our normal time tomorrow? Yes, it is. So during class time. So 2:30 to 4:20. I'll start at 2:30. I'll have this screen up. Music will be playing, and I'll type in the chat, like, please type in any questions. I'll give you like 10 minutes to accumulate questions, and then we'll go over them at that time. Okay. If I don't get any questions, I just take the stream offline and say there were no questions. That rarely happens at the start. But if you have any questions during the stream, please populate the chat with them so that I have them. Yeah, that's all I got. So best of luck studying. Make sure you get those assignments in. And good luck. We're all counting on you.